Hey, my name is Theo McKenzie. I'm a graduate student at UC Berkeley, and today I'm going to talk about supportive closed walks and second eigenvalue multiplicity of graphs. And this is joint work with Peter Rasmussen at University of Copenhagen and Nikhil Srivastava, who's with me at Berkeley. So what we're talking about is walks on graphs. So how these are taken is that we start at some vertex, and then we move to another vertex, which is adjacent to the first vertex, then we move it to a vertex that's adjacent to that one, etc. So I've written this two ways. One is just by drawing the movement of the walk. The other is just by listing the set of vertices that we see in order. So what we're specifically interested in during this talk today is walks that are closed. And closed just means that the walk ends where it starts. We want to know what a typical closed walk looks like. So typical just means that most closed walks of a given length have this property. And when we talk about a property of a closed walk, what we're really interested in is what is the support of the walk? Namely, how many unique vertices do we see in the course of this closed walk? So just to be clear what we mean by support, here we're just taking a random walk, and as we go, we keep track of vertices that we see along the way. And moreover, this walk is closed, so it ends where it starts. Okay, so it turns out that this question, which is combinatorial, actually helps us figure out the answer to other questions in mathematics that are more abstract. So let's talk a little bit about these abstract questions that use this, use counting the number of the support of closed walks, and then we'll go back to actually how do we figure out this problem? What is the support of a typical closed walk? Okay, so now let's talk about the adjacency matrix. So the adjacency matrix is just a matrix where the rows and the columns correspond to vertices, and we place a 0 if the two vertices are not connected by an edge, and a 1 if they are connected by an edge. Now, because this matrix is symmetric, the eigenvalues are real, and therefore the eigenvalues can be ordered. Moreover, matrix multiplication corresponds to taking a step in a walk. So you can think about multiplying by the matrix A like taking a step in a walk in the graph. So a way that this manifests itself is that if I take the adjacency matrix A, I raise it to the kth power, and then look at the individual entries, well, the entry corresponding to vertices U and V, well, that just counts the number of walks between U and V. Okay, so shifting gears a little bit, there's this old problem which asks, what's the maximum number of lines in d-dimensional real space that all share the same angle? And this was solved a couple of years ago by this team at MIT in this very nice result. And the thing that I want to highlight is that the condition that they use to differentiate between the different scenarios is actually a condition that depends on an adjacency matrix, which you might find surprising. And actually, the key lemma that they use is that they bound the multiplicity of the second eigenvalue in this adjacency matrix, and actually in any adjacency matrix. So what they show is that for a bounded degree connected graph, that the second eigenvalue has multiplicity at most n over log n, order n over log n. So note that they actually only need to show that the multiplicity is little o of n, but the bound that they actually end up showing is pretty far from all the best lower bounds that we know. So we know that there are graphs which have second eigenvalue multiplicity omega n to the 1/3, but we don't know anything better than that. So there's this gap here between n over log n and omega n to the 1/3. So what we tried to do is we said, well, can we improve this bound from n over log n? And we were actually able to, but we have the extra assumption that the graph is regular. But if you make this assumption, then you can show that the multiplicity of the second eigenvalue in the adjacency matrix is at most n over polylog n. So once again, we have to have this extra assumption, though, that our graph is regular. So regularity just means that every vertex is adjacent to the same number of vertices as every other vertex. Okay, so let's talk about the other conditions, which are the same as the conditions from the Zhang et al. Result. Why do we need these? Well, first of all, why do we need bounded degree? Well, if we didn't have this condition of bounded degree, then the result just wouldn't be true. For example, if we have the complete graph, then the adjacency matrix of the complete graph is just the all ones matrix minus the identity matrix. And this matrix has second eigenvalue multiplicity n minus 1. Okay, well, what about this connected condition? Well, if our graph isn't connected, then once again, we can't bound eigenvalue multiplicity. For example, we can take some small graph, we can create a bunch of disconnected copies of this small graph. Then the adjacency matrix of that larger graph, which is just a bunch of disconnected copies of the smaller graph, is block diagonal, where each block diagonal entry is the adjacency matrix of the smaller graph. So the problem is then that the multiplicity of the second eigenvalue is going to be at least however many copies there are of the smaller graph. So once again, we can't bound eigenvalue multiplicity. Okay, so what about the second eigenvalue? Well, arbitrary eigenvalues can have linear multiplicity. One way to see this is that if I take a graph and then I create two copies of every vertex, and I connect the graph accordingly, then at least half of my eigenvalues are now 0. So we really need to think about the edge of the spectrum rather than an arbitrary eigenvalue. Okay, so once again, this beats the Zhang et al. Result when our graph is regular. But at the end of the talk, I'll talk about how we can remove this requirement of regularity. Okay, so how do we do this? Well, as I mentioned before, the entries of a to the k correspond to the number of walks between given vertices. So what that means is that the diagonal entries of a to the k correspond to walks that are closed of length k. Once again, closed is just, it ends where it starts. So the sum of diagonal entries of a to the k is just the trace of a to the k. And the trace of a to the k is the sum of eigenvalues raised to the kth power. So another way to say this is that the sum of eigenvalues raised to the kth power is equal to the number of closed walks of length k. Okay, so the other instrument that we'll use is Cauchy's interlace theorem. And what this says is that if I take any symmetric matrix, then I take a principal submatrix of that matrix, then the difference of multiplicity in an eigenvalue in the submatrix and the larger matrix, well, that differs by at most the difference in the size of the matrix. So if the multiplicity of eigenvalue is m in the submatrix, then the multiplicity is at most m plus u in the larger matrix. Of course, Cauchy's interlace theorem says something more general than this, but this is the form that we're going to use in this talk. Okay, so let's put this together. So as we said, the diagonal entries of a to the 2k count closed walks of length 2k. So to be clear here, now we're switching from talking about length k to length 2k. So we just condition on the length of our walk being even. That makes our calculations much easier. So we take our original graph and then we delete vertices at random. If a closed walk has high support, so namely it reaches a bunch of different vertices, then that closed walk will be deleted with high probability once we delete these vertices at random. So what happens then if we assume that most closed walks have high support? To be super clear about what I'm talking about, let's look at this graph at the bottom. So here I have some graph on 6 vertices. I have a vertex u. And what we're doing is that we have 2 closed walks emanating from u, the purple walk and the blue walk. Well, when I delete these 2 vertices, the vertex on the left, and then the vertex on the bottom right, then I delete the blue walk because I've deleted a vertex that contains the blue closed walk. However, the purple closed walk survives because I didn't delete any vertex that is contained in the purple closed walk. So what we want to show, though, is that most of these closed walks are deleted if I delete vertices at random. Okay, so regardless, what do I have left? So let's call S the set of vertices after deletion, and A sub S is the principal submatrix on S. Then the trace of A sub S to the 2K just counts the surviving closed walks on S. But what we said is that we've deleted most of our closed walks when we did this random vertex deletion. So what that means is that the trace, which just counts the surviving closed walks, is now low. So what we claim is that the trace is actually low enough to imply that the multiplicity of lambda 2 is low. And then by Cauchy's interlace theorem, the multiplicity of lambda 2 in A is low as well. Okay, great. So we showed how if we can control the support of closed walks, we can actually bound the multiplicity of the second eigenvalue of the adjacency matrix. So now we'll go back to what I was talking about at the beginning, which is how do you actually show a bound on the support of these closed walks? So keep in mind that we have this closed condition, right? So if we don't care whether the walk is closed, then there are methods that already exist that we could have used, like something like a random walk Chernoff bound. We'll show you what the typical support is of one of these walks, but the closed walk means that we can't use something like that. Okay, so what we end up proving is that almost all closed walks of length 2k on a regular graph of bounded degree have support omega k to the 1/5. So specifically, it's polynomial in the length of the walk. Specifically, what we prove, and maybe this will help giving some intuition when I try to show some parts of the proof, is that for a given number S, the number of supports of length 2k that have support at most S is little o sub k of 1. So it can be an arbitrarily small fraction, sk goes to infinity, of the number of closed walks of support at most 2s, for S equals O of k to the 1/5. So note that this second expression implies this first expression. Okay, great. So let's do a little warm up now. So let's talk about the path. So let's assume that this path emanates, for all intents and purposes, infinitely in both directions. And let's say that we're looking at closed walks starting at this center vertex here. So what is a closed walk on the path? Well, at every step, we can either go left or we can go right. And all that we need is that we're conditioning to start back where we started, to end where we started, rather, because this walk is closed. So this is related to a Brownian bridge, if you know what that is, or combinatorially, you can just think about it as I'm adding a series of plus ones and minus ones, but I'm conditioning on the overall sum being 0. So this is known typically to go maximum distance at most square root k from where we start on a walk of length 2k. So we said, okay, this is great. Well, maybe we should just try to show that the distance typically goes polynomially away from wherever we start. But distance actually isn't enough. We really need to think about support. So the example that really shows this is what we call the bulb tree. And we have this bulb at the top. And what we do is that we start at some vertex within the bulb. And then we look at the number of closed walks emanating from this vertex. And the problem is that because this top part is so well connected, that the closed walk doesn't like emanating down the graph. And sorry, down here, you can think about this as just like being an infinite tree, an infinite arborescence emanating from this small compact object at the top. And the thing is that because this object at the top is so well connected, that closed walks typically don't travel more than distance O log of k on a walk of length 2k. So we can't just consider distance. We really need to talk about support. So what we end up doing is that we say, okay, let's fix a support. So given a support S, we find a support T that contains S such that the number of closed walks on T is far greater than the number on S. So how do we do this? Well, let's take the induced subgraph on S. So the induced subgraph on S is going to have vertices which are maximal degree on the induced subgraph and vertices that are not a maximal degree on the induced subgraph. And note that this is where we use regularity very strongly. The thing is that on any vertex that is not of maximal degree, we know that there is a vertex that is not contained in S that is adjacent to that in the overall graph. How do we know that? Because the overall graph is regular. So that means that if I have some vertex that is not of maximal degree, then there's another vertex outside of the graph that I can connect to that original vertex. So the way that I construct T is I take all the vertices that are not of maximal degree, and then I extend each of them to a vertex that is not in the graph. So T, you could think about as our original vertex set S union whatever the set of boundary vertices are. So really you only need to extend one vertex per boundary vertex. There could be more, but all we really need is one. Okay, so how do we actually show that there are more walks on T than on S? Well, how many walks are there on S? So that's just this quadratic form where what we do is we start our walk at U. So that's represented in this quadratic form by the elementary vector on U. We then remain within S for 2k steps. So that's represented in this quadratic form by just taking the adjacency matrix on the induced subgraph of S. So that's just the principal submatrix on S and raising that to the 2kth power. And then we end our walk again at U, and that's just represented by using the elementary vector on U again. So this is a quadratic form. So this quadratic form has value at most lambda 1 of a sub s to the 2k. And this can be thought of as an estimation of this quadratic form. And what we claim is that this estimation is actually good enough. That if we can show that for this larger set T, that the top eigenvalue satisfies this inequality, lambda 1 of AT raised to the 2k is significantly greater than lambda 1 of AS to the 2k, that shows that there are many more walks, closed walks on T than on S. Okay, so how do we do this? Well, if the entries of vertices of non-maximal degree in the normalized eigenvector sum to some small number epsilon, then what we claim is that we can quantify the amount that we get by extending at each of these vertices, the amount that we increase lambda 1 by extending at these vertices based on the value in the top eigenvector. So intuitively, the way that this works is consider this to be the top eigenvector. So here's our set of vertices, and the size of the circle at each vertex is its value in the top eigenvector. So what we claim is that if the value on the sum of all of these boundary vertices is not that small, then what we can do is that we can shrink all of the sizes of every vertex in our set, and we can take what's ever left over and add it to vertices that are outside of the set to create a new normalized vector. And the claim is that the amount that this increases the spectral radius is bounded by the size of entries of these boundary vertices. Okay, so what we're actually able to show is that the sum of entries of non-maximal degree in the normalized eigenvector of lambda 1 of A of S is omega 1 over the size of S squared. And the way that we do this is a random walk argument that involves electric flows. I'm more than happy to answer questions about that if you have any. So what this shows, putting these two things together, is that the spectral radius, so lambda 1 of A sub t, is at least lambda 1 of A sub s plus c over the size of s to the fourth, where c is some constant. And this is what gives us the previous result about the larger number of closed walks. Okay, so just giving an example here, this is something that we were worried about in our research, which is the lollipop graph. And the reason why we were worried about it is that we know that the entry in the top eigenvector of the vertex at the end of this tail is exponentially small. But the key thing is that if we think about this as a subset of a regular graph, then we can extend at all vertices in the middle here, which create this exponentially small tail. And if we do this, then the total amount of increase is still polynomial, because the sum of the values in the top eigenvector on this tail is still polynomial. So this may seem like a slightly wonky way of doing things, but it turns out that our results are actually tight, in the sense that there are graphs such that the sum of entries of vertices of non-maximal degree is theta 1 over s squared. And the thing that I just want to highlight about this graph is that both the diameter and the size of the boundary are ordered the size of the overall graph. And this is really the only case where our result is tight. And in fact, in our paper, we give our bounds in terms of the size of the diameter and the size of the boundary. Okay, so earlier I said that we could generalize this result to non-regular graphs. But the thing is that our generalization is for the normalized adjacency matrix. So the Jiang et al. Result is for the non-normalized adjacency matrix. Ours is for the normalized adjacency matrix. So it just happens that these two matrices are equivalent when the graph is regular. So that's why we beat the result when the graph is regular. Otherwise, the results aren't comparable. The other way that our result generalizes beyond what I've expressed is that it's actually, we bound the number of eigenvalues in a given interval, and we can actually bound eigenvalue multiplicity for any index, as not just to any index, as long as the index is less than or equal to n to the 0.99. So just these edge eigenvalues near the edge of the spectrum. So what's worth pointing out is that when we generalize to this interval, our result is actually tight. So for bipartite Ramanujan graphs, the number of eigenvalues in this interval is n over polylog n. I said that the result is tight. This exponent could not be tight, but in terms of n over polylog n, that part is tight. Okay, just ending with a couple of questions is the support that we get tight. As we said, for the path, it's omega, it's theta k to the 1/2. I imagine there are other examples where you could do worse than that, but the question is whether omega k to the 1/5 is actually tight. And then the other one is whether you can actually improve eigenvalue multiplicity to O of n to the 1 minus epsilon. So as shown on the previous slide, because of this, when you look at the interval, that this multiplicity can't be achieved. It seems like you need something stronger than the tracial methods that we used. But nevertheless, still seems like a very interesting problem. Okay, so just to conclude, we can bound the multiplicity of eigenvalues of the normalized adjacency matrix. The key ingredient was bounding the typical support of a closed walk, and this is done by controlling the entries of the eigenvector of lambda 1. Thanks a lot.